Hi everyone, I am Abhinav and today we'll be discussing the 26th problem from the CP-31 sheet by TLE Eliminators under the 1500 rated problems. Let's begin. We'll move on to our CP-31 sheet and we can see that the 1500 rating mark is checked. Let's move on to the 26th problem, which is cut them all. Okay, so let's read the problem statement. You are given a tree with n vertices. Your task is to determine the maximum possible number of edges that can be removed in such a way that all the remaining connected components will have even size. Okay, so basically you are given a tree having n vertices and then you need to find out that what was the maximum possible number of edges that can be removed from that tree, so that after removing those edges, the remaining connected components that would be remaining in the tree, they should all have even size. Okay, so you need to remove maximum number of edges so that it satisfies this condition. Okay, and this is the problem statement. So if you look at the first example, so if we move on to the first example, n is given as 4. That means it would have 3 edges. Okay, so for any tree, you know there are always n minus 1 edges in a tree. So this tree has these 3 edges. So from 2 to 4 there is an edge, and from 4 to 1 there is an edge, and from 1 to 3 there is an edge. Okay, so this is the tree given to us, and in this tree you need to remove the maximum number of edges, so that after removing these edges, the remaining tree has the all the connected components in the remaining tree are of all even size. Okay, so let's say what possibilities do we have. Let's say we remove this particular edge. So if you remove this particular edge, then in the tree what we are left with is this component having a size of 2 and this component having a size of 2. Okay, so both of these components have an even size, so this is a valid removal. Okay, so 1 can be your answer if you are removing this one edge. Okay, let's say you also remove this edge. Okay, then what you would have is you will have this component having one node, this component having one node, this component having two nodes. So these components you can see have odd size. So this is not a valid removal. Okay, or what you can do is, let's say you remove these two edges. Still you would have these two components have a size of 1. So this is not a valid removal again. So the only valid removal here in this tree was removing this one edge. So your answer here was 1. The maximum number of edges that you can remove here was 1. Okay, if you look at, let's say, this test case. Okay, so we have a tree from 7 to 1. There's a edge from 8 to 4. There is an edge from 8 to 10. There is an edge 4 to 7. Okay, from 4 to 7 there is an edge. Okay, so I think we should write the tree like that, from 4, 8, 10. Okay, then 6 to 5. Okay, from 6 to 5, then 9. 9 to 3. Okay, again 9 and 3 are different. 3 to 5. Okay, so this is connected like this. Okay, and 2 to 10 and 2 to 5. Okay, so from 10 you have a 2 and from 2 you are connected with 5. Okay, so this tree is something like that. If you, okay, like this is the tree given to you. You can like arrange it like a tree, but this is the entire tree that is given to you. Okay, now for this particular tree, you need to find that what is the maximum number of edges you can remove in this tree, so that the remaining tree has only even sized components. Okay, so what you can do is, maybe if you like remove this edge, obviously there would be a component with a single node, so that won't be valid, so you can't remove this. Maybe you can remove this edge. Okay, you still have a component of size 2 here, and if you look at this component, let's say you keep this as size 2 and remove this edge, keep these two, let's say, and remove this edge, and maybe keep these two and remove this edge. Okay, so how many edges did you remove? You removed this particular edge. I think from 2 to 5 there was an edge and this was an edge. So basically you removed 1, 2, 3, 4 edges from here, and still you had this of size 2, this component 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 of size 2. So you had all the components having even size even after removing these 4 edges. So this 4 is, it still has even sized components. So answer for this test case was 4. Okay, so I hope you would have understood what is being demanded from the problem. Now let's look at the, and then we'll try to think about the logic. So n is up till 10 to the power 5. This is the constraints for the problem. So n is up till 10 to the power 5. That means what all time complexities are acceptable. You can have something like an order of n time solution that would be well accepted for 10 to the power 5. Even something like adding an extra log n time would be fine, and log n would be something like 26, 27. But if you go to something like order of n square, that won't be acceptable, because then you would have like 10 to the power 10 operations which are not allowed in 1 second. You can even go up till an extent of n root n. That would also be just less than 10 to the power 8 operations only. So these you can say are your expected time complexities. So you need to solve the problem somewhere in these time complexities. So basically n root n is very rare for these type of problem. You won't have some root n complexity, but you need to basically solve the problem in some linear time. Okay, so how do you solve this problem in some linear time? That's the question. So if you analyze, what you need to do is, you have a tree. Okay, so let's take some random tree. Okay, let's say you have a tree. Now in this tree you need to remove some of the edges, so that in your final tree you only have connected components with even size. Okay, so first thing to notice is, whenever you remove an edge, you're not removing any node. So basically, whatever components you are breaking this tree into, finally the sizes of all those components, if you look, then the sum of the sizes of all those components would be the size of the original tree, which is n. Okay, so you know, obviously whatever components you would have, let's say the sizes of these components are k1, k2, k3 and so on, then you know that the sum of these sizes would always be n. Okay, and what your requirement is, that all these components, all these case would have even size. That means the sum of these sizes, if all of them are even, then this n should also be even. So if you are given an odd n, the first thing that you can conclude is, if this n is only odd, then you cannot divide this odd number into parts so that all of the numbers are even. Okay, whenever you divide an odd number, you would get an odd number plus an even number whenever you divide it. So you would always have at least one component which is odd if you are starting with odd number of nodes. So you would, whatever, if even if you don't delete an edge or delete any of the edges, you would never have that condition satisfied where all of the edges, all of the components are even sized. So for that, like you are given, if you have to print -1 if it is impossible to remove the edges to satisfy the property. So for odd n, you would always print -1 as your answer. That is it. Now, when your n is even, you need to solve the problem when your n is even. So when your n is even, one way is just don't remove any of the edges. You would have a single component of even size. So zero removals is always a valid answer when your n is even. But what you need to do is, you need to maximize the number of removals. So how do you maximize the number of removals? So let's see which edges can you remove. So whenever you remove an edge, okay, first of all, whenever you want to analyze a tree, always root the tree at some particular node. So when you look a tree in the rooted form, then you can like use some properties in the tree and use some algorithms in the tree. If you have a random tree, you can never use anything. Okay, whenever you apply DFS, BFS or anything, you need to have a rooted tree. So whatever tree you have, let's suppose we root the tree at node number 1. You would always have a node number 1 there in the tree. Let's suppose you root the tree. Let's suppose we suppose the tree rooted at node 1. Okay, so when the tree is rooted at node 1, now whenever you remove an edge, what would happen? If you're removing this edge, this subtree, okay, the subtree below that edge, okay, so when you root this tree, then for every edge there would be a node on top of that where you would have an edge. So like you have n minus 1 edges in a tree. So apart from the root node, every node would have a edge on, like you can say, on top of it. So this edge can be represented by this node. Let's say apart from the root node, for all the n minus 1 nodes, you have an edge on top of that. So if you want to remove the edge on top of this node, then the subtree for this node, this is the subtree represented by this node. Then if this subtree is of even size, then you can say that you can remove this. The whole tree was of even size, and then you have divided this whole tree into this subtree and this remaining tree. And if this is of even size, then a total even minus even, this remaining part would also be even. Okay, so whenever you remove a subtree which is of even size, the remaining tree would also be even if you're as you already know, n is even only. So n is even, we are solving the problem only for even n. For odd n, you have already answered. Answer is minus. So for even n, whenever you have a subtree of even size, you can remove this edge. Okay. Now, once let's say you removed this edge, this at an even size of 4. Okay. Then next, what edges can you remove? So let's say you again remove one more edge from here. So initially you had computed this subtree size, which also, like, this subtree was also included there. But when you are removing this edge, you don't know what all edges are removed from that subtree. So if you remove this edge, what are you doing is, whatever was the size of this subtree, from that this is already removed. But if this whole subtree was even and this even subtree was removed, then this thing was also even. So basically what you need to check is whether this is even or not, but it's same as checking whether this whole subtree is even or not, because you are only removing those edges where the subtree below it is even. So what you can do is, for every node for which the subtree is even, you can remove all those edges. So if 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so and plus 4, 16. So for this particular node, this subtree has a size of 4, and for this particular edge, or for this particular edge, this whole subtree had a size of 16. But when both of them are removed, you are dividing into this subtree of size 4, this subtree of size 16 minus 4, and this remaining subtree of size n minus 16. And n was also even, so 1, 2, 3, 4, 5. Okay, let's say you have one more so that n is even. So this is also of size 6. So you can see all these three components are of even sized, and you can remove more number of edges. So just check for every edge whether the subtree below it is even, remove it. So you can remove all those edges if the subtree below it is of even size, because by removing them you are only dividing one even component into two even components. So you can keep on dividing a even sized component into two even components until you can like do. So you just, so basically you just need to find for every node the size of the subtree. If the size of the subtree is even, remove that edge. If the size of the subtree is odd, don't remove that edge. It's like that simple. Okay, I hope you got why this is working. Now how do you compute the size of the subtree? It's a basic DP problem now for a DP on tree problem in order to compute the size of a subtree. Okay, so you'll initially only compute the size of the subtree, and then at last you can just check whenever you get an even size subtree, you just add a +1 to your answer or just remove that edge. Okay, so you can do that afterwards. First, you can just pre-compute the size of every subtree. So how do you pre-compute the size of every subtree? Run a DFS. Inside the DFS, you can say that, like, you can use a DP or a size array, which is like a DP. So size I is basically the size of the subtree under node I. Okay, so if this is the ith node, then this is a subtree we are talking about. Size I represents the size of this subtree. So what we can see, that if we are talking about the size of this subtree, we can just move to all its children, and whatever are the sizes of its child components, sum of those sizes plus 1 for this. So this is the DP transition. Size of I is 1 plus the sum of size of j, where j belongs to the children of I. Okay, so this is the DP transition through which you can just compute the size of every size of the subtree for every node, and then finally your answer is just the, like, for computing the answer you can just run a for loop for I from not from 1, because there is no edge on top of the root node, but for all the other nodes there is an edge on top of that which you can remove. So you will start from I is equal to 2 up till n. So I is equal to 2 to n. You'll run a loop, and then if the size of the subtree I is even, you just add +1 to your answer. You can just do your answer plus. That's all you need to do. Okay, just pre-compute the size for every subtree using this DP, and then just move from I is equal to 2 to n. Whenever the size is even, add a +1 to your answer, return your answer. Okay, so the overall time complexity for computing this DP using a DFS would be order of n time for computing this, and again order of n time for computing this. So overall, in order of n time, you can solve this particular problem. Okay, I hope the logic is clear to you. Let's move on to the code. Okay, so in the code, what I'm doing in the main function, I take the input n, and in an adjacency list I'm storing the tree. Okay, so uv and u dot pushback v dot pushback u, because it's bidirected edges. So I've stored the tree in an adjacency list, and then if initially only I see that, okay, this was our input part. Okay, and then initially only if I see that the size of the tree is odd, then I'll just print -1, return out. My job is done. And if the size of the tree is even, then we would run a DFS to compute the size of every subtree. So we'll initialize the size DP or the size vector with 0, or we'll assign it, and then we'll run a DFS. Inside the DFS, we'll initialize size as 1 and add all the size of the children to it. Okay, so we are running a DFS, and we are computing this DP. Sorry, we are computing this using this DP transition 1, which is stored initially, plus for every children we add the size of the child. Okay, the size of the child gets added for every children of the node u. Okay, so this way we are computing the size of every subtree. Once that is done using DFS, then we can just check from I is equal to 2 to n. If the size is even, add a +1 to your answer. Okay, so from 2 to n, if the size is even, do answer plus. Okay, this is done, and we print our answer. Okay, if you analyze the time complexity from the code, taking this input was taking order of n times. Okay, and then this is just an if check, and we return out if we are done there only. Then this DFS is overall, this is a DFS, so its time complexity would be order of n only, and we are computing this DP here only, so this DFS would take an overall time complexity of order of n, and then this for loop is running n times, so order of n here as well. So overall time complexity, you can say, is order of n only. Okay, and if you look at the space complexity, then this adjacency list is taking a space of order of n, and this size vector is also taking a space of order of n. So the space complexity is also order of n. Okay, so I hope the problem is clear to you. It was a really nice tree problem where you had to just crack this small logic that you can remove an edge if the size of the subtree is even. Then calculating the subtree size is a very standard DP on tree problem, which I hope you know. Okay, so I hope you understood the problem. Thank you so much for tuning in.